4 handouts up here. We're on. Welcome to EE282. This is Computer Architecture and Organization. If you're coming from the computer science side, it's probably also CS212, and we're going to be exploring the wonders of building high-speed microprocessors mostly, with lots of other tidbits along the way. You probably haven't seen my face around here very much. This is actually a kind of deja vu experience for me, because about 20 or maybe 22 years ago, I was sitting probably in that seat over there, taking EE282 from, I think, Ed McCluskey, who was teaching it at the time. And fear not, this is not the same course that he taught 22 years ago, because computers have changed just a little bit in the interim. So it's been updated, and this is going to be a lot more like 282 taught last semester than 282 taught 20 years ago. But I was a graduate student in computer science here in the mid-'70s, and hung around for longer than I'd like to admit. Eventually got out with my PhD, went off to Carnegie Mellon University, taught there for a short time, just over a year, and then escaped from academia. I went into the real world, as I say, and came back to California, helped start a couple of different companies, and for the last 15 or 16 years have been involved in building products and selling things based on computers, hardware and software. And I've decided to come back and see what academia is like after all this time. And I'm looking forward to this, and I think it should be fun. And hopefully you'll learn something in the process as well. There are 4 handouts, which hopefully the SITN people have already gotten. Can somebody in SITN get back to me? Let's see if the two-way connection is working and if you got any of the handouts. Is anybody out there? No? I guess we'll find out later on. There should be 4 handouts. They all went out supposedly in time for all of the SITN sites to have received them. If that's not working, then get in touch with the people at SITN. Tanya Tarver, I think, is the one who's in charge of handout distributions. And if they're not getting to your site, find out through her why they're not. The other thing you might check is that they might physically be getting to your company, but for some reason they might not be getting to the place where you know about them. So check your mail room and things along the way. Yes, somebody's in. Hello? Nobody there. Okay. If anybody from SITN decides to let us know that they're there, please do that. The first handout has some information about me and the course and a proposed schedule, and this is a tentative version thereof. Probably next Tuesday we'll be distributing an updated version of this. You can see that a lot of the variables here have yet to be assigned values, but some of them are right. That's me. My email is shustek@ngc.com. My office for the time being is in ERL 443, which is next to the department office, and I will be having office hours right after this class for an hour or for as long as people want to come by. So if you're interested in coming by to talk about stuff in the class, to talk about what it's like in the real world, to talk about scuba diving in New Guinea, anything that sounds interesting to you, come by, and I'd be delighted to chat with you. I have both a phone number there and as well a phone number at my place of business, so you can try either one, and a fax number here if you want to send to me by fax. Probably email is the best way to get in touch with me. I assume everybody here has an email account, and that works pretty well. Certainly for the people out in SITN, they're welcome to send me email, but as well to call during any of those times. You can call my work office almost any time. We are privileged for this quarter to have 3 great TAs, all of whom have TA'd this course before. If you're here, guys, why don't you come up and let them get a bead on you and see what you look like. These guys will be your lifeline for all sorts of things. It's David Heine, who did it, I guess, 2 quarters ago? A while ago. Okay, Albert Chang and Len Hammond, who I guess did it more recently. You did last quarter. They can be reached also at through email. Anything else you want to say before you disappear? I've got the mic. Okay. Thank you. There is an email account for the TAs, EE282 TAs at ogun.stanford.edu, and that's probably the best way to get in touch with them. They will all have office hours. We don't know where and when at the moment, but probably by next time, and certainly by next Tuesday when you get an updated version of this information sheet, we'll know all of that information. Course support, secretarial support, administrative support is available from Lily Wan, who's in the office next to me. She comes in at 10:30, leaves at 3, so if you need to talk to her about handouts or getting duplicates of things, you need to be there during those hours. Back handouts are in a rolling file outside Lily's office, so if there's anything you're missing, you can get it there. If you need to get returned homeworks or exams that you didn't pick up in class, they'll be there for you to pick up. Other thing I should point out to the students here, you probably know this better than I do, that we are being broadcast. Therefore, the SITN students won't hear you if you ask something in class unless you pick up the mic and use the microphone, and most of them apparently work, not all of them. Most of the time I run with interrupts enabled, so whenever I'm talking, if you want to ask a question, just holler out, in SITN, beep your microphone button, and I'll usually respond to the interrupt. And I think that works pretty well. I tend to run courses fairly informally, so please do the same. Happy to receive input, get questions, comments, suggestions, and so forth. Any questions or comments or suggestions so far? This material. Okay. Let's talk a little bit about what this course will cover. It's a course in computer architecture and organization. And basically, a pretty amazing thing has happened in the last few years, which is that computer performance has increased a remarkable amount. And one of the main focuses of this course, if we can get the overhead, that would be handy. One of the main focuses of this course will be to try to understand where that recent performance growth has come from, and understand what the trade-offs are in making the design of computers, in particular in microprocessor-based design. And in fact, that's one of the differences between the course as taught now and the course as taught 20 years ago. 20 years ago, people were focused on mainframes, big computers, because that's what people were designing, and now the course is focused almost entirely on microprocessors, what you can put in a single chip. Now, it turns out there's not that much difference. It's kind of amusing to watch over the course of the history of microprocessors, starting in, I don't know, 72 or 73, how it's basically been reproducing the evolutionary stages of the mainframes, and that not all of them, but many of the clever innovations that gradually were added in the 50s, 60s, and 70s to mainframes are now being added to microprocessors as the density of integration and as the complexity of the chips increases. The course outline goes something like this. We'll begin talking about how one measures and evaluates cost and performance in computers. And in some fundamental sense, that's the only thing that matters. Since about, I guess, the 1930s, that's really been the only thing that matters. Does anybody know what happened in the 1930s to make that true? It was theoretical work. Basically, people like Turing and Kleene in the 1930s discovered and were able to prove that you can compute any computable function with a machine that's absolutely trivial. And if that's true, why are we bothering to spend all this time enhancing computer architectures and making them better? I don't know how many of you have seen the design of a Turing machine, but a Turing machine is an awfully trivial machine that basically can read a location, write a location on a big tape. I see some people shaking their heads. They've seen what they are. And although as a software engineer for many years, I would hate to be given the task of actually having to program that machine, it is in fact the case that that can do everything that the latest and greatest, Pentium or P7 microprocessor can do. So in fact, what you gain from all of the advances in computer architecture is an increase in performance or a decrease in cost in one of those two. And that's therefore why the focus of this course is going to be on that. The instructions are the things which are the intermediate between the hardware and the software. And we're going to be talking about principles by which those instruction sets are designed and go through several examples of different styles of instruction sets. I'm sure you all know that there has been a revolution in the way instruction sets are designed in the last 5, 8 years, something like that, with a movement from complex instructions, which reached their pinnacle probably about 1977 or 78, into a reduced instruction set, so-called, a simpler instruction set, which in some ways is harder to program, but makes the machine run a hell of a lot faster. And that makes a big difference. And there have been some other changes in compiler technology that make the disadvantages of that new style of computer less annoying. After you design an instruction set, you've got to do something to implement it. And it turns out the single most important technique that has been used recently in making an instruction set run fast is pipelining. And we'll be talking probably for 5 or 6 lectures about basic pipelining, advanced pipelining, all of the techniques that have been used in some of the most recent microprocessors to get those instruction sets to work as quickly as possible. And in fact, there's a great deal of interaction between the design of the instruction set and its ability to be pipelined. Pipelining is not a new idea. It was introduced probably mid-late 60s, something like that, but it was introduced on machines whose instruction set did not lend themselves easily to be executed quickly in pipelining. The change to the new instruction set allows pipelining suddenly to take on a much more important role in making the memories go faster. Okay, so you get the computer to execute its instructions real fast, but then we've got a problem here. Computers have gotten fast at a remarkable rate, but unfortunately memories have not gotten fast at that same rate. If you guys want to graduate from Stanford and make $1 gazillion, the thing to do is to figure out how to make big, fast, cheap memories the way people are making fast and cheap microprocessors. Nobody knows how to do it. So the next best thing is to try to take the relatively slower memories that we do have and know how to make and somehow fake it, make it look like they're fast memories. And the way to do that, of course, is to make a hierarchy of memories, and you've probably all seen caches, and we'll talk a lot about the use of caches to bridge this gap between very high-speed processors and relatively lower-speed memories. There are lots of tricks that can be done to make that work well. In addition, there's another gap, which is a gap between what the application would like memory to be, which is infinite, and what the hardware has to make memory to be, which is finite and of finite speed. And virtual memory is a technique, again, to fake something that we would like that doesn't exist in real life, which is an infinitely large memory at infinitely fast speed. Of course, we can't achieve either of those things, but we can get closer. Having built a computer, then, that executes with instructions in memory, you've gone somehow to get things in and out of it, and we're going to spend a few lectures talking about disk subsystems, what they are, how do you get things in and out of these super fast processors at a reasonably fast rate, and in particular we'll look at the disk subsystems, because those are the ones for which performance is a very important factor. There are other, if we have time, I/O subsystems that would be nice to explore, like video subsystems or audio multimedia kinds of gadgets, and what effect the addition of those kinds of resources has on the basic design of I/O systems. And then at the end, depending on how much time we have and how fast it goes, I'd like to talk about a couple of different things. We may do 0, 1, or 2 of these. Interconnect technology survey has to do with how it is that you connect these fast processors together to make an ensemble which tries to be n times faster than n computers running separately. Obviously, this has been a sort of holy grail that people have been searching for 25 years. And you're given a processor, it runs a job at rate X. If you've given 2 processors, how is it that you can get it to run the job at 2X? Or given 100 or 1,000, how about 100X or 1,000X? Well, it's very hard, and the problem is basically communication between the processors, and there has been a lot of work done over the years and a lot of good work done recently on scaling up the interconnect to match the high speeds of the processors, and if we can, we'll talk about that. I guess I've in that discussion actually talked about both of these issues. One is the interconnect, how to get processors connected to each other at high speed, and the other is how then do you build multiprocessors? What's the configuration of the processors that you build using that interconnect. So the basic theme is, if you're a computer designer, how you make the decisions using cost and performance as the basis for deciding the best way to build your computer. This is just a quick demonstration that things are going remarkably fast. This is a privileged point, actually, I think, to be involved in the design of computers, because things are getting so fast, so quickly. And back in 1978, the cost for a computer, the cost per million instructions per second of a computer was about $1,000, and now it's $500 or some number like that. That doesn't mean that for $500 necessarily you can buy a computer that executes 1 million instructions per second. But for $2,000, you might be able to get a processor that executes 4 million instructions per second, and you can probably go down to Fry's over here and do it. This really is remarkable because you can buy now for a couple of $1,000s what it cost millions of dollars to buy just 20 years ago. Now, one of the interesting questions is, how long can this go on? How close are we to fundamental physics limits that will prevent us from taking this any further? That's an interesting question for philosophical speculation that you can come to my office hours and we can talk about. Generally speaking, we're several generations away from reaching the physical limits, the limits having to do with physics. So probably for the rest of your careers in designing computers, that's not going to be a problem, and this curve will likely continue for quite a while longer. This curve is driven in part by the technology, by the ability to build smaller transistors and put more of them on a single chip. But it's also driven by two other concerns, factors. One is that we've been better at designing the architecture of the computers built out of those transistors, and the second is that we've made a lot of strides in compiler technology that take better advantage of the new architectures. And that's produced this remarkable advance. This is just for chuckles. It's not the case that everybody knew that it was happening, and I was collecting some quotes going back as far as 1835 for people who said that computers were either worthless or pretty close to worthless. George Airy was actually a very smart guy. He was the guy, for those of you who are astigmatic like me, he was the guy who, among other things, invented the lenses that correct for astigmatism. But he was presented with a proposal to fund Charles Babbage's analytical engine, and basically he was in the position of the NSF or something these days, and basically said that it was a worthwhile piece of junk and shouldn't be built. And I think he was wrong. This is a famous one from president of IBM saying that the world could use about 5 computers. But as recently as 1977, Ken Olsen was quoted as saying there's no reason for any individual to have a computer in his home. I'll bet he has a computer in his home now. Let's talk a bit about what it is you should know before taking this course. Basically, what you need to know is fundamental internal computer organization. W182 is certainly an adequate preparation for this course. How many of you have taken 182? Looks like about a third, something like that. Equivalent course or experience will work as well. What we would like you to know in particular is roughly how one builds a synchronous logic system out of gates, flip-flops, registers, data path, and control. Now, we're not going to be doing that at the gate level, but you need to understand what a flip-flop is, how combinatorial logic is, what's the difference between combinatorial logic and logic that has actually stored values in it. Understand how multiplexers and ALUs work for moving data around and computing on data, and what a state machine is, how one takes that assembly of wires and flip-flops and sequences it through a series of operations that has a desired result. Now, you don't need to be able to design your own computer. You just need a familiarity with how those things work in general. If you have any questions about whether your background is appropriate for this course or whether you're going to be in trouble or not, talk to me or talk to one of the TAs, and we'll find out what you know and what courses you've taken and where you've taken them, and figure out whether we think you're going to have too much trouble. On the software end of things, you ought to be familiar with some assembly language. It doesn't really matter what. We'll be going over several different assembly languages here. If it's the first time you've seen an assembly language, you're probably going to be in trouble. So you should have had some exposure to programming in anything, 68,000, MIPS, 8086 type architectures, so that you understand how that goes. You also need to be able to program in a high-level language. And again, anything will suffice. C is probably the language which is preferred. There'll be 3 programming assignments I'll talk about in a second. The third one will in fact be in C. The first 2 will be in a language that you probably have no experience with, but will give you a crash course in everything you need to know about that particular language. Any questions about what you should know? Let me talk about some things that we will not be covering, because you either have taken it somewhere else or you will take it somewhere else, and in any case is not specifically relevant to this course. One is computer arithmetic. We won't be talking about how numbers are represented in the computer for fixed point or for floating point. We won't be talking about algorithms for doing multiplies or divides or floating point or signs or any of that. You also don't particularly need to know it for this course, other than knowing how generally integer ALUs work. So you can either have taken that or take it later. We won't be talking about the design of particular ICs. This is not an IC design course. This is a computer architecture course. We'll be talking about what those ICs ought to do, but not how it is you're going to build them. I don't think I will ever draw a picture of a transistor or a resistor in this course. We're also not going to be very practical. And this is not a course where at the end of it you're going to be able to walk out and go down to Fry's and buy yourself a 64064 or something and build a computer out of it. There are going to be no wiring diagrams that have pin numbers here. Although that's fun. So sometime I would recommend that you actually do that, but we're not going to be doing it here. We're not going to be talking much about microprogramming. That used to be a big issue in the bad old days of mainframes as a technique for making faster and cheaper computers. And it's still used in various ways. In fact, some of the more recent RISC chips have a kind of microprogramming in them that we may allude to, but it's not exactly the same as it was in the old days, and in any case, we won't spend very much time on it. VLIW designs, actually, we may be able to spend a few minutes talking about that. Those are very long instruction word designs. It's sort of next generation after RISC, if you will, a way of making machines go even faster. And some of the very latest implementations of some of these RISC architectures are using that, and we may or may not be able to spend a few minutes talking about it. Okay, the textbook. The textbook is a very good book written by John Hennessy, who's at Stanford. I think he's in fact the chairman of the computer science department this quarter, or right now. And David Patterson, who's at UC Berkeley, both well-known both in academia and in industry. They've been involved in the design of chips and processors. And they wrote a book about 4 years ago called Computer Architecture: A Quantitative Approach. We will be using a beta test version of the second edition of the book, which is a paperback, and it's available in the bookstore, and it costs you only $33, which is about half of what the real textbook costs. But it's a beta test book, which means it has some bugs in it, has some inconsistencies in it, page numbers and references are wrong, and figure number references are wrong, and so forth. But it's certainly worth using the second edition instead of the first edition, because there have been a lot of changes. If you have the first edition, don't use it. Get the second edition of the book. You really do have to do that. You get a discount, by the way. I forget exactly how it works, but I think they give you $30 back on a purchase of the final edition when it comes out, hopefully sometime this summer. The book itself has a regular structure for each chapter, where they have an introduction, then they talk about the principles. Toward the end, they have a couple of interesting sections. One is a putting it all together section that gives you real examples and tries to evaluate real processors, and they talk about chips and manufacturers and computers, and it's not just theoretical. The section after that is the fallacies and pitfalls section, which is fun reading because it tells about the things that don't work and the assumptions that people make about how to build computers, and give examples that are sometimes embarrassing to the computer industry as a whole, and I guess also to individuals who were responsible for things that they had high hopes for that didn't work, or various fiascos. And then they also talk about history. This book tends not to emphasize history very much, unlike some of the prior textbooks that were mostly just case studies. But I'm fascinated by the history of computers myself. Actually, the first computer program I ever wrote was in 1962, and I brought a piece of the computer that actually ran that program. For those of you who don't recognize those little glass ampules on top, those are vacuum tubes. Before the days of integrated circuits, there were transistors, and before transistors, there were vacuum tubes. And this circuit board represents one flip-flop. This is one bit of information. The other thing which was a problem in these days was that a computer that did anything at all reasonable had about 10 or 20,000 of these tubes. And the lifetime of these tubes is a year, maybe 2 years at best, something like that, 4,000 hours, 5,000 hours, 10,000 hours. And if you have nothing to do on your way to walking to the next class, do some calculation in your mind about, given a computer with 20,000 tubes, if the average lifetime of each tube is 2 years, how long is that computer going to run before one of the tubes burns out and the computer stops working? The answer is not very long, and that was one of the serious problems. But I think looking at history actually is interesting from a couple of points of view. One is that you can learn about things that were done that didn't work, or things that were done that do work and in fact are useful to reinvent. I talked about this motion toward RISC processors as a new revolution. Well, in fact, the IBM 650 was very much like a RISC processor. Let me do this for 30 seconds, and I'll stop talking about ancient history. But the IBM 650 had an opcode that was 2 digits, which was a decimal machine, and a memory address, which was 5 digits, and another memory address, which was 5 digits. And in fact, this is exactly the kind of fixed-width instruction that was reinvented with the RISC technology. The CISC technology, the complex instruction streams, wound up inventing instruction designs that were incredibly complicated and very long, and we'll see them later, and that in part contributed to making them execute very slowly. The new RISC machines go back to the kind of instructions that were done in the early days, where they were all fixed width, easy to decode. In the old days, it had to be because there wasn't much hardware to decode them. In the new days, it's because you can get the machines to run faster by doing it. So it was a very simple architecture. Unfortunately, it didn't run very fast because the tube technology was very slow. It also had no random access memory. The only memory in this computer was a rotating drum. All of the instructions and all of the data was stored on a drum. And in fact, each instruction had within it the address of the next instruction. This memory address was the address of the next instruction. And the way to get your computer program to run fast was to arrange the sequence of the instructions so that as each one finished, the next one about to be executed was just coming up under the read head of the drum. And in fact, there were automatic programs to reshuffle the instructions of your program. One of the nice side effects of that is that, in fact, in those days when computer programs were submitted as punched card decks, if you dropped them on the floor and they were out of order, you could shuffle them together in any order whatsoever and put it back in the machine, and it worked just fine. Because each instruction had the address of the next instruction. Of course, it would run a lot slower. Okay, so what's different about this course compared to other courses that have been done? We've talked about some of this. The book is called A Quantitative Approach to Computer Architecture. What's the non-quantitative approach? Well, that's a sort of case study approach. You study lots of old computer designs, you try to separate the bad decisions from the good decisions, but it's hard to figure out what metric to use to make that decision unless you're trying to be precise about quantitative measurements of performance and cost. Of course, one way to measure the success of an architecture is the marketing approach. Was it a business success? And for better or worse, real life intrudes upon the computer architect, and sometimes the computers which are technical successes turn out to be commercial failures, and vice versa. We'll see several examples of both cases of that as the course goes on. But the quantitative approach uses real-world measurements to evaluate design alternatives. Now that's actually, from a philosophical point, an interesting thing to be doing, because after all, computers are not something that exists in nature. They're something that we created. Why is it that we have to make measurements on them as if they were unknown gadgets that we did not control? And the answer is that it's very easy for human beings to make assemblies of systems that are more complicated than you can predict the performance of. And in fact, you wind up, in doing quantitative measurements of computers, treating them as if they were something that existed in nature. Another example is the economic system. The economic system, after all, is the product of our minds, and why is it that we can't understand and predict what it's going to do, but we certainly can. What we'll be doing a lot of in this course are simple back-of-the-envelope calculations. This is not a course in queuing theory. We're not going to be doing any higher mathematics. As important as those things are to be able to do some rough order of magnitude estimates of whether things are going to be better or worse when you make a particular change to a computer. And there are very simple calculations that we'll be using to predict those things. When you can't predict those things, then you have to fall back to writing simulators for machines that don't exist or for modifications of machines that you want to make. And you'll be doing this in the programming assignments, both predicting the performance of various architectural features and modifying the performance of existing simulators. John McCarthy is one of the patron saints, I guess, of computers, and I noticed on the internet that he puts it at his signature at the bottom of all his contributions to bulletin boards. He who refuses to do arithmetic is doomed to talk nonsense. And I think there's a lot of truth in that, and part of this course is to get people to do some simple arithmetic to avoid talking nonsense when it comes to computer evaluations. Okay, course mechanics. There will be assignments. There will be problem sets almost weekly, which means about 7 or 8 of them, something like that. There'll be 3 programming assignments. The first 2 of them will be in Verilog, which is a computer simulation language, and the third one will be in C. The first 2 will have to do with taking a model of one of the RISC processors, a MIPS-like RISC processor. The first programming assignment, in fact, will be pretty easy. We'll give you a model of a RISC processor that has intentionally been buggered, has bugs placed in it, and your assignment will be to try to find the bugs and fix them, make it work. And they'll be pretty simple things. The point of this exercise is very much to get you familiar with Verilog and the mechanics of running simulators and so forth. The second programming assignment is a bigger one, where you take a model like that and, in fact, make it pipelined. We'll give you a model which is not pipelined. You make one which is pipelined and make sure that it executes correctly. You can work in pairs on the programming assignments and on the problem sets. And if you work on pairs and problem sets, just submit one with both names. The late submission policy is that for within the quarter, for any assignments, you get 2 free late days. And after that, we deduct 20% per assignment per day. There will be an exam, 2 exams, a midterm and a final. Tentative times for them are midterm on February 14th, 7 to 9 p.m. And for the final, March 21st, 7 to 10 p.m. That time may change because I think they've assigned us a different time in the course schedule. Grading.
I think the final is from 3:30 to
3:30 to 6:30, okay? Subject to change, but that's our best guess so far. Grading. You guys aren't interested in grades, right? You're all seniors and graduate students. You're here for the information, you know, right? Okay. I'll try to take grading seriously. When you get out in the real world, grading tends to be something that one doesn't take as seriously, but I'll try to take it as seriously as you do. Roughly speaking, the distribution will be 20% for the problem sets, for the homeworks, the 7 or 8 homeworks, 30% for the 3 programming assignments, 25% for the midterm, 25% for the final. There will be review sessions. They have yet to be scheduled. The TAs will be handling the review sessions. There'll be some on Verilog. There'll be at least one on the before the midterm, one before the final, and maybe some others. I should say just a couple of words, 30 seconds worth of discussion about Verilog. In your career as computer scientists or engineers, you will learn lots of languages. You probably all know a lot of them already. So the idea of having to learn a new language at this point shouldn't be very daunting to you. But there are some languages that have something very special about them, and it's worthwhile trying to learn a representative language from each of those sets to see what they're like. And Verilog is one of them. Verilog is a simulation language. It's an event-driven simulator, and the distinctive characteristic of it is that unlike normal programs where things happen in sequence and you write a sequence of statements and the statement further down on the page gets executed later than the statement further up on the page, in Verilog, it ain't necessarily so. Verilog tries to model the way the hardware works. And the way hardware works is that everything happens at the same time. You change within speed of light propagation delays. You change a signal on one side of the chip, and pretty soon later a signal is going to change on the other side of the chip. It's not making its way in sequential access from one side to the other. Verilog tries to model that. And I'm talking about it now only so that you can begin to think about it, because it really is a paradigm shift in the way you think about doing programming. In Verilog, you can write a statement like a variable A has a computed value from B plus C, and someplace later in the program you write a statement that says that D is a computation based on A and E. And you don't expect this statement to be executed at the same time this statement is executed. But in fact, in Verilog, that kind of thing can happen. As soon as you execute this statement, then this statement will take effect, even though it's somewhere else off in the text of the program. So things are happening sort of simultaneously. And the way that you get things not to happen simultaneously is to explicitly say that they should be delayed. So you say something like, 5 cycles later, I want the signal A to get the value of what signal B was. And that gives you some insight into, in fact, how the simulator itself is working. It's called an event-driven simulator because it keeps a list ordered in time of what things should be happening. When you give it a statement like this, it puts on its list for 5 timer ticks later that this statement should be executed. But in the meantime, all other statements that are to be executed at this time tick are done essentially in parallel. Now, in real life, of course, they're not done in parallel, but they're done in some arbitrary order. Enough said about that. Just for you to think about, the TAs will be holding a review session on Verilog, and you'll learn more than you ever wanted to know about it. This is an electronic classroom. I assume you all have access to email. There will also be a news group, which you all need to read. If you don't have the ability to do that, you need to find out how to do that. It's su.class.ee282. And that's primarily going to be used by the TAs as a mechanism for posting general information, clarifications, and so forth. Nothing to prevent you from posting on it, but you know, try to keep your posts limited to things which you think are interesting to the group. I think this particular slide is not in your handout, so don't trouble the papers. In the introductory handout, it has some of this information. It has the name of the news group. I mentioned that the TAs will have an email account. As a point of email etiquette, it would be nice for you to include in the subject line of anything you send to them what the reference is about, homework number 1, problem number 2, and so forth, so that the TAs can route it to the right person, because all 3 of them will be reading that account. Don't try to ask general questions that require essay-type answers, like, how does the cache work from the TAs on the electronic mail mechanism. If you've got those sorts of fundamental dilemmas, it's important to resolve them. Come talk to us. Talk to me, talk to the TAs. But don't expect the TAs to be able to write a textbook online. For the people out on SITN, it is possible, in fact, to use Internet to do the programming assignments, but there may be difficulties. The simulators use X windows, and there's often a problem getting X client server stuff to work across the Internet because of the way people set up firewalls and so forth. You can certainly run the simulators through the Internet without the X Windows debugging stuff, but you'll be losing some of the facilities. For those of you local here, that shouldn't be a problem. Grading. We are looking for graders, and in fact, graders can come from the class. So any of you who want to get out of having to do the homework assignment can volunteer instead to be a grader. And you learn equally as well from marking other people's papers as you do from trying to do it yourself, I think. And we probably need 3 or 4 graders. If you want to volunteer to do that or try it out, see how it's like, come talk to me or talk to one of the TAs or talk to Lily, and we'll sign you up. That's actually a pretty fun thing to do. Oh, one thing I should mention. The first homework number 1, which was handed out, is due, try that again, on next Tuesday, just as it says in the tentative course schedule, but don't do the last question. Sorry? Don't do number 2.7, the last question on the homework. Actually, you can do it for your own amusement. The problem is that it's a little bit ambiguous, and it's going to be a hard thing to grade. We decided not to do it, not to assign it, so you're welcome to do it, but we won't be requiring it. The tentative course schedule will be revised for the next version of the handout, and if you have any questions about it, I'll be happy to talk about it. Okay, let's talk a little bit about what computer architecture is and what is this thing that we're going to be spending our time on. Generally speaking, computer architecture is just the hardware that executes programs, but it's convenient to break it apart, in fact, into 2 different parts. One is an abstract design of an instruction set, and some people call only this part the architecture. That's the part of the design of the computer that the machine language programmer sees. The instructions, how they work, what the registers are, all the visible stuff. And it's the official boundary between the software and the hardware. IBM used to call that book the principles of operation for any particular machine. And it had nothing to do with any particular implementation. It was only a description of what the programmer needs to run a program on that particular kind of computer, although there may be many implementations of that computer. The implementation is a particular hardware design which executes those instructions. And you can build multiple implementations for the same instruction set design. That actually was a concept that didn't occur to the world until the mid-60s, and the first computer series that was intentionally designed to separate the architecture from the implementation was the IBM 360 series, and came out in the mid-60s and had a very strict definition of what the instruction set architecture was, and then the engineers were free to do whatever they wanted in implementations to design machines ranging from very slow machines to very fast machines, and it was and is a successful architecture, the IBM 360, 370, 390 series continues to live on and is probably in danger of becoming the longest-lived instruction set architecture ever. The implementation part itself you can also consider divided into two parts. One of them, and the part that we'll be talking about, is the organization. What are the building blocks? Where are the registers? Where are the caches? Where are the data pads? The memory components and so forth? And how does one plug them together? How do you sequence them? And so forth. With a particular organization, you're also free to implement that in several different technologies. That hardware logic technology is not something we're going to be talking about here. That's logic design, circuit design, how do you actually build flip-flops, NAND gates, and so forth. And then other peripheral things like how do you package it and how do you cool it and stuff that turns out actually to be very important, but this is the subject of other courses, not this one. I remember back when I was a student here, one of the highlights of the W380 seminar series was having Seymour Cray come in, who had just finished designing Cray 1, which is at the time the fastest and best machine in the world, and everybody was talking about it. And he came here, and we expected him to talk about the design of the processors and the instruction set units and ALUs and so forth. And what he seemed more pleased about in the design of that machine was the copper extrusion that they had used to get the cooling fluids to flow through the columns of the circuit boards. And as far as he was concerned, one of the important innovations in that machine was not the organization or the logic design of the hardware, but the plumbing, the cooling system of the machine. And it turns out that those are very important considerations. Even now, for the design of integrated circuits, one of the major constraints in putting more and faster circuitry on a single chip is how do you get the heat out of that chip fast enough so that it doesn't burn itself up. This distinction between architecture and implementation has become slightly less crucial in recent days. In fact, the RISC-type machines have gone back a little bit to the philosophy that you're allowed to change the architecture somewhat with each new implementation. And the reason we can do that now and not have such a trauma about it is because programs are written in high-level languages. And if you change the instruction set architecture, but also change the compiler to know about that change, then all of the programs written in that higher-level language won't have to change. That's still not wonderful, in fact, because that loses binary compatibility, and this floppy disk you had with a program already compiled that would run on one Spark machine may not run on the next Spark machine because, in fact, instruction set architecture has changed and have to recompile it. Just realized I've been switching between large and small here. Where is this stuff that we're looking at compared to the world of computer systems? Well, the answer is we're only looking at a very thin layer. We're looking at the layer between the hardware and the software. And one could argue, in fact, that it's the most important layer, but we will be looking at instruction set and hardware organization. Below that is logic design and electrical design. Above that are operating systems, middleware, environments, applications, and so forth. All of which are wonderful things to concentrate on, but not something that we're going to be looking at. We're also constraining ourselves in time. We're not going to be spending a lot of time looking at old machines, and we can't spend a lot of time looking at machines that haven't been designed yet because none of us have crystal balls. So in a sense, we're limiting ourselves vertically in the organizational aspect and horizontally in the time aspect to a few years surrounding now. But it's okay. There's plenty of interesting things to do even with those constraints. We can be bounded in a nutshell and count ourselves king of infinite space. Anybody know where that came from? One of the things we need to do in designing computers is to figure out where to make the trade-off between hardware and software. This is fairly straightforward stuff, I think. Given particular functional requirements, how do you decide what you ought to do in hardware, what you ought to do in software? For example, if you're building a multimedia computer, should you put video decompression in the hardware, or should you put it in software? Well, there are trade-offs. Obviously, for hardware, the advantage almost always is speed. There also may be an advantage in consistency of implementation because it's harder to change the hardware, and the implementations will exist for a long period of time. But software is is more flexible. There are some who would argue that it's easier and faster to design, although I think that that's not true. And having done both hardware and software design, software is just as difficult and often even slower to design than hardware, so I don't think that's true. There may, in fact, be a lower cost of errors. I think probably everybody in the Western world knows that Intel had this little problem with division algorithm on their Pentium chip just recently, and that little problem, which is probably, I don't know, 16 flip-flops or 16 bits of information, is going to cost them about $500 million maybe to fix. If it had been a software problem and they could get around it by shipping everybody a floppy disk, it would have been a very different problem. But software is slow, which is what leads you to implement things in hardware. But hardware is expensive and hard to change, as in that example. In fact, there are no scientific ways of making these trade-offs. It's a mixture of engineering disciplines and aesthetics and marketing, and getting it right is probably the hardest part of doing computer design. Okay. We said that we were going to use cost and performance to evaluate computer architectures. What is performance? What does it mean to measure performance? There are two possible interpretations. One is the response time. I give a computer something to do. How long does it take for that thing to come back? You know, if I'm sitting in front of an ATM machine, an automatic teller machine, and I punch the button that says "Give me some money," how long do I have to wait for the money to start spitting out of the machine? Even there, it's not sure what time you ought to count. In an ATM machine, I'm counting elapsed time, but in fact, for the design of computers, you might want to count only the execution time of the CPU and not the time spent doing other things, like transmitting the request to and from the teller machine and so forth. The other measure is throughput, which is what's the total amount of time, total amount of work that's being done by that computer system. What's the bandwidth? That's a useful thing from the system point of view, and if you're a system designer, that's something you have to worry about. Obviously, from my point of view as a user of the ATM machine, I don't really care how many thousands of other people's transactions are being processed at the same time. I'm interested in the response time. The people who are responsible for that computer system are interested in the throughput primarily. They're interested in the response time only insofar as it makes me angry. An example is a car wash, which may have different throughput and latency requirements. A car wash, if it starts a car every 30 seconds and holds 6 cars, this, by the way, is not a theoretical presentation, because I went down to one of our local institutions, namely Lozano's, and timed how long it takes cars to go through their car wash. If a car wash, as they do, starts a car every 30 seconds and holds 6 cars, what's the latency? How long does it take a car after it enters to come out? Anybody? I can't hear you. 2.5 minutes? Well, okay. That's subtle response I think you're making there. Actually, 3 minutes is how long it takes for the car to get out. And the throughput is what? How many cars per second are going through? Anybody? 2 cars per minute. Yeah. This is all pretty trivial stuff. But the point is mostly to understand that there are these 2 different ways to measure performance, and you can speed up one without the other, or you can speed them up both together. If I take that ATM computer system and I add more computers processing lots of jobs in parallel, in the absence of queuing effects, it probably won't increase my latency because my job has to go through the same amount of steps. But the throughput is going to increase because more people are going to be able to have their jobs processed simultaneously. Okay, let's get a little quantitative, and this is all kind of grade school arithmetic stuff, but it's actually worth doing because you would be amazed at how many mistakes are made even in the literature about trivial things like this. What does it mean when we say that computer X is n% faster than computer Y? Well, the easiest way, at least for me to understand it, is that the difference in performance between the 2 machines compared to the performance of machine Y is n%. Multiply by 100 and you get n. Where performance is a rate kind of thing. It's how fast the computer is running, how many jobs per minute, instructions per second, whatever your metric is, that's what you try to measure. So you're comparing, it's a ratio of something that computer X is doing to something that computer Y is doing. You're comparing to computer Y. Now notice that performance and execution time are reciprocal. Speed up the performance, the execution time goes down. So if you want to compare computer X to computer Y in terms of execution time, which is a great way to do the measurements, if you substitute 1 over execution time for performance, you get an equation that says the difference in execution times divided by the execution time of X is the performance, is the amount by which computer X is faster than computer Y. Notice that we're dividing by the execution time of computer X, not by the execution time of computer Y. It's pretty trivial, but a mistake that's made an amazing number of times. You'll get a chance to, on the homework, make sure that you understand how that works. Notice another small fact, that saying that that X is n% faster than Y is not the same as saying Y is n% slower than X. Right? Because you're dividing by a different denominator. So if it takes X 10 seconds to do a particular job and it takes B 12 seconds to do a particular job, X is 20% faster than Y, 10 minus 2 over 10. But Y is 16% slower than X. This is true, and this is wonderful stuff, and all of you folks are going to be engineers and want to produce the right results. If, on the other hand, you go to work for the marketing department, then you're welcome to be creative with your statistics. And just for your amusement, this is a book that was published about 50 years ago, something like that, which is a very non-technical book called How to Lie with Statistics. It's actually a classic. I think it's even still in print. And it's a delightfully funny book. It's quite non-technical, that talks all about how to generate statistics that intentionally mislead people. So I don't intend to describe any of those techniques, but if you're interested in doing that, or you're interested in seeing how it's done, to recognize it or to avoid it, you might want to pick up this book. It's a good half hour's amusing read. Any questions, comments? It's all pretty easy stuff. In fact, the first 2 lectures are all pretty simple, in part because it's a review of some stuff I think that has been done in 182, also in part because I know there are people going to be coming and going in the course in the first 2 weeks, and we don't want to cover any really earth-shattering stuff in that time. But this stuff is nonetheless important. One of the, again, obvious rules in designing computers is that if you want to make it go fast, you take something which is done very frequently and you make it go faster. Make the common case go fast. It turns out to be the best thing to do because it's the easiest way to make computers go fast, and it's often the case that it's easier to make the common case go fast than to make the non-common cases go fast. And you can do the non-common cases, like the exceptional traps in software, like arithmetic overflow. Don't design your hardware to do arithmetic overflow traps if it doesn't occur that frequently. You can do it in software. It has all the other advantages that we talked about of doing things in software. And you can spend your precious resources, both chip area and time, design time, making the more important things go faster. People, amazingly enough, sometimes don't do that. And it's very easy, especially in instruction sets that have very general instructions, like call instructions on 486, which are incredibly complicated, an Intel 8486 type chip. If you try to optimize the general case of those instructions, you will wind up spending a great deal of time, a lot of chip area, for something which in general is done very infrequently. In fact, there is a subset of that particular instruction which is executed extremely frequently. The thing to do is to concentrate on that subset, identify it to begin with, and make that go fast. Forget about the rest of it. As I mentioned, it's easier, so the design time is faster, and it tends to be more flexible. The idea, and it gets back to the current fad in doing RISC chips, is that the hardware should provide fast primitives, and Everything else, if possible, should be done in software. Let's go over, again, trivial quantitative example of making the common case fast and a decision process that you might have to go through in deciding which of two possible enhancements to a computer to make. Let's say you have a computer that does floating point arithmetic, and you have the option of speeding up the floating point divide 8 times or speeding up the floating point multiply 2 times. Which would you choose to do? Well, without any other information, the answer is, I don't know. And the other information you need to be able to make that decision is what % of the time is currently being spent in typical programs that your customers are interested in running in doing floating point multiplies or floating point divides. So let's say that 30% of the time is spent doing multiplication, 8% of the time is spent doing division. How do the numbers work out? Well, if you speed up multiplication, then that 30% of the execution time now takes half the time because we speeded up multiplication 2 times. So one way to think about this is if the program took 100 seconds, then 30 of those seconds were multiplication. You just threw away 15 of those seconds, so the execution time now is 85 seconds, or 85% of what it was. So the new hardware is 18% faster than it was. Notice we divide by the right number, so we get 18%, not 15%. Now what happens if you sped up division? Division is 8% of the execution time. It becomes 1%. Sounds better, right? It's an 8 times faster speed up. But the new execution time is now only 93% of the old execution time. And you took out 7% of it. So the hardware is only 7% faster versus 18% faster. So obviously do the multiplication, not the division. Now there are other, obviously other factors that go into making these kinds of decisions in real life, including how difficult is it, what is the likelihood of making a mistake, in having the division not work right, how important it is to the marketing department to announce that you have these features, what your competitors do, how much chip area it takes, and so forth. This is one of the factors that go into making these decisions.
Sorry?
Yeah.
Is that working? I don't know.
It's working, sounds like it.
Okay. So how feasible is it to get data like that for general purpose processors? I mean, like what % of the time we spend on doing that? Or
the answer is it's very feasible. It's not easy sometimes, but it's very feasible. The most difficult part of getting information about how much time is being spent is deciding what set of programs you're going to make those measurements on. Which customer base are you going to include, and what programs are they going to be running? Once you've decided what the typical application is, you can run simulators, you can instrument existing machines, you can put probes in there to measure how often floating point multiplies and divides are done, and so forth. Actually doing it turns out not to be a problem. It's time-consuming sometimes, but that's why places like SLAC hired graduate students like me in the 1970s. In fact, one of the things that I was working on when I was a graduate student was instrumenting what was then a microprogrammed machine to capture statistics about instruction execution and try to figure out how often things are done. So it's very important. It's relatively easy to do, and the hard part is figuring out what programs to run. Any other questions? Okay, so you all believe, and it's trivial, that we should make the common case fast. And the question is, when do you stop doing that? What's the limit on the speed up that you can get by making those common cases fast? And Gene Amdahl, who gets his name on a law that describes that, is again one of the sort of patron saints of computers. He was working for IBM back in the 60s, and in fact had a lot to do with the design of the 360 instruction set. Then went on, obviously, to found the company in his name. But his name is also used on this law that says that the amount of improvement that you can get by enhancing a particular feature is limited by how much that feature is used. Sounds obvious, but the other way to look at it is that the amount of effect you have by making something go faster is limited by how much time that feature is not being used. The new execution time of the computer that you've just added this enhancement to is the sum of two parts. It's the execution time that is unaffected by this whiz-bang feature that you just added, plus the execution time of the part that is affected divided by how many times you sped it up. So if you multiply up by a factor of 8, then the amount of time that multiply was being done divided by 8 is how much it's now taking, but the other stuff is unchanged. So the overall execution, if we say that the fraction from 0 to 1 of the amount of time that feature is used is fractions of enhanced, then 1 minus fractions of enhanced is the fraction that it's not being used, and fraction of enhanced is the fraction that it is being used and is the part that's eligible for speed up. So the speed up, which is the old execution time divided by the new execution time, is 1 over the sum of those two factors. The 1 minus the fraction enhanced, which is the old part, the unenhanced part, plus the enhanced part divided by its speed up. Pretty simple, but sometimes produces surprising results. You'll get to surprise yourself with some of the results in the homeworks, but here's an example. In fact, this is an example in the same spirit in which Amdahl originally proposed his law. He was discussing issues of how to speed up computation using parallel processors. When you do that, you have to be aware that you can do parallel processing for part of the computation, but not all of the computation. So let's work through a typical example. Let's say that an application that you want to speed up using parallel processes is almost entirely parallel. 90% of the computation is parallel. So we expect to have a big win from designing a machine that uses multiple processors. Well, let's see if we do. Let's say that we're using P processors. The fraction of the time that we're going to enhance the execution during which the parallel processors will be used is 0.9. So the speed up is 1 over 0.1, which is the part left over, not being paralleled, plus 0.9 over P, which is the part that's being sped up. Well, run through the calculation. It says that if you use 10 processors, you get a 5 times speed up. Not a factor of 10, but not so bad. But if you use 100 speed ups, 100 processors, 10 times as many processors, you don't even get a factor of 2. You've sped up from 5.3 times to 9.1 times. And if you use 1,000 processors, you only get barely a factor of 10 speed up. In fact, it's pretty obvious that if you use an infinite number of processors, the best you can expect is to get a factor of 10 speed up. And that's probably not what your marketing department in this computer company expected when you told them that almost all of the application can be improved by parallel processors. So the moral is that the common case will change depending on what you've done to speed up the computer. And once we've sped up the computer by introducing a number of parallel processors, we'd better do something else because otherwise we're wasting our time. And here's an example of the something else. Let's say, again, that we had the same model, that we're speeding up 90% of the computation by adding parallel processors, and we add 100 parallel processors, and we get a speed up of 9.1. Now instead, let's say that we take that other 10%, the non-parallel part, and we speed that up by only a factor of 2. It's a much better thing to do, because now that 0.1% that was left over from the parallel processing goes faster by a factor of 2. We still get the 90% going faster by a factor of 100, and the whole machine is going faster by a factor of 17. So now you can go back to the marketing department with some evidence that you should get to keep your job. This may be stretching it a bit, but another form of commonality is in addition to commonality of things that are done very frequently, or parts of the computer that's used very frequently, are pieces of the memory that are used very frequently. And it turns out to be recognizing that is a great way to speed up computers. You've probably all seen this. Memory reference patterns exhibit two kinds of locality. One is spatial locality, which is to say that locations in memory that have been referenced recently imply that locations in memory close to them are going to be referenced recently. Now that's a big win once you recognize that. That means that you can do anticipatory reads. You read location X, Even though the computer didn't ask for location x plus 1 or x minus 1, you read it anyway, anticipating that it might be used. Lots of the time, that turns out to be the case. For instructions, because of sequential instruction references, obviously they execute in sequence, branches, and we'll see measurements to support this later, tend to be relatively short. So wherever you're executing now is probably close to where you're going to be executing later. For data, array references can be the same thing. If you lay out the array in memory correctly, and you access it in sequential order, then those memory references will be in sequential order. It's also instructive to note that it's easy to reverse subscripts on array manipulation programs to destroy the effects of caching because you've destroyed the spatial locality. Now a column of a vector, instead of being in sequential locations in memory, might be splattered across a megabyte worth of memory, which makes it much more difficult for caches to take advantage of the spatial locality. Temporal locality says that if you referenced a piece of memory recently, then chances are you're going to reference it again. For instructions, when you have programs in loops, obviously that's true. The hotspots are things that ought to be put into caches. For data, stacks and variables that are referenced and re-referenced also represent temporal locality. And there, the design of caches, which I'm sure you've seen, are such that if you reference a memory location, put it in memory, keep it there for a while, chances are it'll be referenced again. That could be a loss. I mean, if you consider a program that executes and references a sequence of 1,000 memory locations, and your cache happens to hold 900 memory locations, it's going to be a bad thing to do to keep the most recently used 900 memory locations in your cache. And a dumber algorithm that would keep the first 500 that you ever referenced in memory is going to make that program run faster. So this whole issue of what the patterns are of temporal and spatial locality and what algorithms you ought to use inside the caches to make it work best is going to be something that we're going to be talking about a lot in the second half of the course. We're about out of time. I'll stop here. If there are no questions, see you on Thursday.